to our final speaker for today. And it's really last but not least, I was really delighted to meet Tom Würdinger actually last night. And we started chatting. And what's really amazing about Tom is that he is actually an entrepreneur at heart, but he's a top scientist. It's one of those rare combinations where you really have all these different skills combined together. So Tom started when he was 17, 18 with a business. He actually, his dad was in the logistics business and he felt he could solve some problems. So he had an import-export business at the age of 17. And then at the age of, he was actually importing scarecrows, i.e., you know, what are called vogelverschrikkers, which worked really well. And then he thought, I can do that well. I can actually also put my hand toward, you know, importing and making some good money, potentially, out of lumpia-vellen, i.e., you know, spring roll skins. So he was really diverse, got some businesses off the ground, but actually then had a chat with his mother and he said, shall I study law? And she said, that doesn't sound good for you. So he embarked on the study of medical biology. He did his PhD in the Netherlands and then moved to the US to do his postdoc. Came across some amazing people technologies and made some fantastic discoveries before coming back to Holland, where he then set up ThromboDX. And after that, another company that he's going to tell you all about right now. Please give a very warm welcome to Professor Tom Würdinger, who's going to tell you about his science and his business activities. Thanks, Tom.
Thank you so much. It's a pleasure being here, and I'm happy to discuss with you all the things that happened this year with the acquisition of the company that we set up only a few years ago. As Anna introduced, I did some earlier business in a totally different field when I was about 18. So the past 20 years, I tried to reposition myself a little bit. Let's see if this works. I see myself now as this. So I'm specialized in molecular biology, but I also specialize in oncology, virology, bioinformatics by now. I've been working at different institutes. I started doing medical biology at the VU University. Then I did my PhD at Utrecht University, then moved to Massachusetts General Hospital and Harvard Medical School, and then back to the Cancer Center Amsterdam, where I have this fantastic research group. This is my team in the Cancer Center Amsterdam, and they're very important. This is my creative brain, and they helped me to build this company detecting cancer in blood, and they continue to do so, and they continue to develop all sorts of new technologies, but also context and content. We try to avoid focus in this lab. It's purely based on creative minds putting new technology to work, finding new applications. We try to focus on cancer, but some of the technologies that we develop also work for cardiac disease, for neuroscience, and neurological issues. So this is a very important team to me. As said, I think we have been adapting the team more towards bioinformatics and systems biology the past 3 years. We try to work on science fiction, where we think that it should be possible not to have cancer as a chronic disease, but to cure cancer. We think that should be the goal. You don't want to put a goal saying, we want to make cancer a chronic disease. No, we want to cure cancer. And we believe to cure cancer, you should detect it early as possible, because if you treat cancer late, it's quite hard, way more hard to cure than when you detect it early and treat early. There are numbers floating around that say that if you detect cancer early, 80% of current cancer deaths can be prevented. And that's a huge number. So you can come with a new cure against cancer, and you may cure 1% of the cancer, or prevent 1% of the cancer deaths, but why not change to this plan B? Try to detect cancer early, in a way that we prevent metastases and try to treat when it's only local, by surgery, by radiotherapy, and by the current therapies that may work very well if you treat early. To detect cancer early, you want to screen us, healthy people, feeling healthy at least. Because if you want to catch cancer early, you want to catch it when someone is healthy. For that, you want to have something that is very easy to do, and we think that blood would contain the information. There are some other people, Asimov wrote a very nice book about this, who say that it would be possible at some point in the future to travel through the blood, through our body, and see what's wrong, if there's anything wrong. So we decided to engage into blood-based diagnostics. Actually, last year, MIT put together a top 10 of breakthrough technologies. And one was the Internet of DNA, connecting everything, a global network of genomic files. So we can learn from the genetic aberrations of person A for the treatment of person B. The other thing is these liquid biopsies. So we thought, well, maybe we can even combine that. We're not the only one who think this. Basically, the field is exploding, and many companies are actually focusing on blood-based diagnostics to detect cancer. Not always to detect cancer as early as possible, also for therapy selection, for differential diagnosis. We started ThromboDX, that was back in 2011, and we focused on a component in blood which is called platelets. And blood platelets, you know, because if you cut yourself, it's those platelets that cause clotting and a crust to form. But platelets do much more. They're the most abundant cell type in our blood, but they don't have a nucleus. The interesting thing is, if you have cancer or cancer cells in your body, the platelets are being manipulated. They change their genetic profile by biomolecules released by the tumor cells. And this we call education of the platelets. So we call them tumor-educated platelets, or TEPs. There are many more biosources. For instance, vesicles, there's plasma. There's all kinds of biosources in the blood that you can use for the detection of cancer, but platelets was not yet being looked at, and that's why we really went for that, and it's turned out to be really successful. So we published two stories. The proof of concept story was published in 2010 and 2011, and then last year we published in Cancer Cell the large story where we profiled platelets of hundreds of patients. This story led to a lot of media attention, where they would say that we can detect cancer in a drop of blood, which is totally wrong, because we don't detect it in a drop of blood. We detect it in a tube of blood. It's the equivalent of a drop of blood that we use ultimately for the test. But those specifics are often lost in media. The interesting thing now is that we have these various biosources, multiple companies that all think their biosource is the best. Well, I don't think there is one biosource that is the best. I think you want to collect all the biosources in one deck of cards, in one shell company, and then make the best test that you can think of. So here they say, let the tap dance begin. So a little time frame of what happened to us and this company. And in 2011, we got the first publication, and we generated the IP, the patents. It's a patent umbrella. In 2012, we incorporated ThromboDX, got a license from the university, and set up a team, and this was very important. Again, the team, it has been mentioned many times before. In this case, the CEO of ThromboDX, Rolf Jan Rutte, was very, very important in closing the final deal. 2013, we generated funding we had no VCs on board. Everything we did was by incubating at the cancer center, relying on government funding, which is very, very important. We got great support there. And this allowed us to build this prototype platform. In 2015, we had a publication, media attention, and then Illumina called and said, hey, this is interesting. You propose to detect cancer in blood, all cancers basically, to allow early diagnostics. And then we said, yeah. And then they said, well, maybe you want to come over and talk because we have a similar idea. And then they told us about their plans to form their own startup called GRAIL. And the mission of GRAIL was to detect cancer early when it can be cured. And it totally aligned with the thing that we were doing. So I think it only took 2 months before our company got acquired by Illumina. Illumina is a sequencing company. It's my dream company, so it was really perfect. We will always rely on the companies that develop the devices that we use for our content. So either we build our own sequencers in this case, or we go for a partnership, or we sell it to those companies. In this case, we truly believe that Illumina was the right company. So, in 2016, Illumina acquired ThromboDX and incorporated GRAIL. And only a few months ago, the tech transfer was accomplished and academic research continued. Now, it is the idea that in 2019, the first test will be introduced by GRAIL. So let's see how that goes. Currently, we are having a research collaboration with Illumina and the Cancer Center Amsterdam. There's 2 Illumina employees actually working in our lab. We have weekly strategic calls, and the ThromboSeq is in progress. And I wanted to show you some of the latest data that we hope to publish very soon. It's actually under review in a great journal, so I really hope that that works. But not before I first give you 2 slides on GRAIL. It's a revolution in early cancer detection. And this was told, we saw all the plans, and we thought, if the platelets could be part of this mission, that would be so fantastic. Big investors are involved, Silicon Valley, we would never be able to do that here. So we really think that GRAIL was the way to go, and I think it's still the way to go. The mission of GRAIL, as I said, is to enable stage shifting of cancer, to get only stage 4 metastatic cancer being detected more early for better treatment. And that would be revolutionary, I would say. That would probably also transform the pharmaceutical industry. Instead of developing all these cures for metastatic disease, we can now focus on developing cures for early disease. So how does the platelet technology, the ThromboDX technology work? We take a tube of blood, we isolate the platelets, then the RNA, we amplify the RNA, and then we sequence that. Then we get tumor-specific signatures. Those tumor-specific signatures are actually the input for our self-learning algorithms. Self-learning algorithms are similar as the search algorithms that companies like Google use. Just our input is genetic code. This is the data that we published late last year. We had about 200 cancer patients, 50 healthy donors. We took the blood, we took the platelets, we sequenced that, and we built a cancer classifier. This classifier was able to distinguish between healthy individuals and cancer patients with extreme accuracies, 96%. Of course, we also identified problems. As with every technology, there is a chance for hurdles, so with this technology. And 4 issues were identified by us and by others. One was that healthy individuals and cancer patients for the development of a test should be age matched, in case age plays a role. These ones were not age matched. The healthy controls were younger. Another issue was blood storage. Differences in blood storage, could that influence the test? People said, include inflammatory conditions, because how can you distinguish between a cancer and an inflammatory condition? Maybe if someone has a pulmonary hypertension, you read it as cancer, and that you really don't want that. And of course, there was this relatively low number of samples. So we decided to tackle these hurdles in one new study, shown here. It's based on lung cancer, all age matched, blood storage matched, including inflammatory conditions, many different ones, and hundreds of samples, giving accuracies still in the high range. Now keep in mind, this is not 96%, it's a little less, but it does include all these weird inflammatory conditions, from multiple sclerosis to pancreatitis, so it's everything's in there. So we thought these results were just fantastic, and we continued with lung cancer, but also with early stage breast cancer, and there we get similar accuracy levels. Here we are now embarking on a large screening study, where we hope to screen women, asymptomatic women, for the presence of breast cancer, in comparison to mammography. Our ultimate wish would be, of course, to replace mammography with a blood test. But let's first compare. This is brain cancer, which is difficult because it's in the brain. Here we can distinguish between early stage and late stage brain cancer. It's just another example where we reach accuracies of about 95%. What else can we do? Not only detection, we wish to detect and select. If we detect cancer, it would be nice to know what to do. In this case, we took the, I think, most hard case, and this is immunotherapy selection. Immunotherapy is great. We had a couple of examples earlier today. For instance, nivolumab, it only works in 20% of the cases, but if it works really nicely. Nevertheless, the costs are huge. So this is a headache. If only we could select or predict which patients would benefit from the therapy and which patients would rather benefit from another therapy, then we would have a hit. So we looked what type of immunotherapy would be most suited. Well, here this is BMS, and these are the share prices after their immunotherapy trial failed. So this is a few $1 billion lost here. So we thought they need a response prediction test, and then they can redo the trial. As a proof of concept, and this is now continuing, we selected patients with lung cancer treated with this immunotherapy. And we had patients that either responded, you see here at baseline tumor. Here after 3 months it's getting smaller. So this is a responder. And here we have a tumor in the lungs, and one after 3 months that's bigger. So this is a non-responder. We had 30 responders and 34 non-responders. We collected the blood before the start of the treatment, and then assessed the patients for responder or non-responder. And then we asked our self-learning algorithm, can you come up with a gene panel and algorithm that will tell us in advance who will respond and who won't respond? And we got to an accuracy of 86%. So now it's 20 and 80%. We have no prediction tool. With a simple blood test, we could at least have 86. So this is something that we're now further expanding on, and together with BMS, we are trying to see if we can turn this into a prediction test. Blood. So the conclusion so far is that the ThromboDX diagnostic platform enables blood-based diagnostics. The technology is reproducible, and large validation studies are in progress. New results will be published, I think, early next year, maybe, if we're lucky, even before Christmas. Of course, they will be available to everyone. So we will try to make them open source, like our previous data, so everybody can have access and see for themselves if this works or not. So again, this is the team and the foundations that provide support, and I thank you very much.
Thanks very much, Tom. I think it's an incredibly amazing story to hear about those developments. I'm sure there must be some questions for Tom. No? Anyone who has one can stand up, and the microphone comes towards you. I have, is there someone? No. Yeah? No, I don't see anyone for the moment. Oh, there? Are you? No, no question. I do have a question for Tom, because he's been incredibly modest. You've been so modest. I love the scientific results, really well done, some great results. But you've been so modest on your business activities. So, you know, essentially you're part of Grail. Is this, you know, I mean, I think it's really been too modest. So Grail did a Series A round in a size that we've never heard of here in Europe, right?
Right. It's 100 million plus.
100 million plus as a Series A round.
Yes.
And you're a major shareholder.
I'm a major shareholder, so we're all waiting for the IPO to happen. That would be, of course, fantastic. But that's not why we sold the technology.
Yeah.
We believe in the mission of Grail, that it's truly possible to do this stage shifting. I think an IPO ultimately will help to generate sufficient funds to make it to that global step.
Yeah.
And I think that will be key. At this moment, there are some very important investors on board, like Bill Gates and Jeff Bezos, that will get us to this first phase, I would say. And Google Ventures also is part of it. Then I think the team they have recruited is fantastic. It's the best of the best people. I was able to be part of the hiring process myself, and they were so incredibly stringent. It's unbelievable. So I'm stringent when I hire my people, try to hire my people, but I was quite surprised to see that of the 5 top people that I selected, they only picked one, the best one, to be hired. So can you imagine that in these early months we had to hire 40, 50 people in 2-3 weeks. And then they say, well, you know, you did your best, but we need better people, even more better people. I thought that was quite surprising that the emphasis was so much on excellence. Yeah,
that is amazing. It just shows how important quality is. Before we move on to the next one, so the next final bit of today, I just wanted to ask you, you know, again, full of young, budding entrepreneurs in the room here, what would be, you know, your bit of advice that you would give to them to actually bring good science into a business environment and make a great success of it?
You need to have a good team, and as was said before, 1 or 2 mentors, key opinion leaders that with whom you really trust, and that I think is very important. A team is very important, and you need to be a bit stubborn, but not too much. Listening is also very important, and then you just need to go for it, and don't be scared.
I think that's great advice. Don't be scared. Big thanks to Tom Würdinger.